So, we were discussing what is the major problem of this QMMM calculation, why the results are even worse than a pure semi empirical calculation. And to understand, you have to go to the fact that how we have selected the QM region. Now, in the QMM calculation, how you select the QM region, there is no very obvious guides. So, it depends upon your chemical intuition where the reaction is actually happening. And if you see the structure again, the main like the interaction is happening between the atom 16 and atom 7. So, the error is actually not intrinsic from the onion process, but it rather stems from a poor choice of the QM region for this particular problem. Since we want to ultimately compute the energy related to breaking of hydrogen bond, this is the strongest bond here, which is our strongest binding point here. A more sensible choice of space should select the atom directly involved in the binding as our high level region. So, this 16 and 7 is involved in the bonding. So, it is maybe a good idea to connect to the nitrogen atom at the adjacent carbon atom, which is related to this one. Now, you may ask why I have not chosen this carbon, but this carbon 5, not this one, because here is an oxygen attached to this. Oxygen is an electronegative atom, so it can have some effect. Similarly, here I do not choose this carbon, but nitrogen, because it can have some electronegative effect. So, this hydrogen, and you need to remember always the cutting of the bond should be done through some single bond there. You should choose the QM region in such a way that it should never cut across a double bond. So, this is the QM region now we are going to use for our calculation. So, this is our new input file will look like. The PAL 16 is a misnomer. Maybe I should remove this one because we have not talked about how to run parallel. Two things to notice here is that you can actually give two separate groups of atom. The atoms numbers does not need to be concurrent, like for here it is 4 to 7 and 16 to 9 that you are giving, and as well as this has to be ended by two ends. One is to end the QM atoms, and the other is to end this one. Max score you may give, you may not give, but let us now do the calculation with this improved onion and see how the binding energies now looks like. So, the way we will do it, I think somewhere we have a complex input file. I made it XTB, but what I can do here is that I can change the topmost part. This is for the complex, and copy paste this part. X2V rev 2 TZ VP, this should look fine, and this I should store as complex improved. Similar thing I should do with the monomer. I have copy paste the same thing and save as monomer improved. Somehow this has been named as monomer improved.txt, but that I can. Or maybe I could have directly changed it from here. This is a Linux command which can rename the file. So, now both of them are here, I can run them one by one. So, first I run the monomer improved, improved dot out. So now I should run the complex improved. So now we can open the output file. So this is complex improve.out. So this is the final QMMM energy. Improved QMMM. For the monomer, it's monomer improved. This is the final single point. One important thing to notice here is that this absolute energies in terms of monomer is quite different in QMMM, XTB and improved QMMM, because the absolute energy does not matter. What is important is energy difference. I think again the minus sign was missing here. So now the value is 8.3729. So if I come here, and as we told that we will take up to 2 significant digits, and the above 2 we can copy paste from the previous table. So now you see, using proper onium you actually get pretty close number to the reference or pure DFT calculation. So now you can see that using proper onium you can get very good agreement with pure DFT or proper onium calculation, and the results are much better than what you get from the naive onium calculation. So the way you select your QM region in a QMM calculation is very important for the accuracy of the calculation, and using a wrong QM region, an inappropriate wrong maybe not the correct word, is the inappropriate QM region can lead you severe error, and your results can be even worse than a normal MM calculation. So how to choose that? First thing, there will be some guidelines which we will discuss, but the first thing is to always make sure that you choose your QM in such a way that it encompasses the chemically important region. Under no condition you should the QM region should be chosen such that it is chosen, it is bonded to an MM atom through a double bond or a triple bond, and always a test is to actually perform the calculation with a certain QM region of your which is chosen from your chemical intuition. Then increase the size of the QM region a little bit more to increase more atoms, and your the energy difference or the property what you are calculating should converge with respect to the size of the QM region. So there will be a place where even increasing the size of the QM region will not make any drastic change in the energy difference or the property you are calculating. In that case, you can consider that your results has converged with respect to the size of the QM region. Now, for the homework problem, you are going to consider the structure of alpha tocopherol or vitamin E, and you can download then optimized geometry, optimized at XTB level from this link. So what you are going to do is that if you in the presence of acidic or basic environment, if you remove 2 electrons and 2 hydrogen from here, one of the methyl group adjacent to the oxygen atom, this one and this one. So, one hydrogen will be removed from one of the methyl group and one of the hydrogen will be removed from the OH group. Then it will, then one of this methyl group will lead to a double bonded methide group, and there can be 2 possible structures. So, this H will remove from OH. So, this will become a C double bond O and this will become a methide group. Now, the methide group can be formed both from, so the other hydrogen can get removed. So, the methide group can come here, which we will consider up, and it can be removed from here, which we will consider as down. So, we are going to calculate the free energy difference between those 2 conformers. So, what you need to do is you need to use BP86 XTB calculation. So, basically DEF2 SVP basis set should be used for the high level method and BP86 DFT method, and the lower level method should be an XTB. Remember, we need free energy. So, first we need to optimize the structure, taking the QM region at BP86 and calculate the frequency, and then from that we can get the free energy calculation. Now, question is that how we are going to choose the which part should be taken as XTB or which part should be taken as a lower level of method. Here we are interchangingly use MM and XTB because this is just used as a lower level of method. So, again the guideline will be same, that I need to do cut the bond where there is a single bond and most probably preferably a CC single bond. So, this is the region I should take as XTB, and so I should cut the bond here. So, I need to take the structure, change this OH and the methylene to generate my starting gas structure using Chemcraft, and then this region by looking at the atom number I will take them as QM, this one as XTB, and then I optimize both the up and down structure, then I will calculate the free energy difference and we will see which one has a higher free energy. So, just to tell the problem again, because this problem is multi-step and little bit more complicated than what we are seeing up to now. So, what we will do is that we will start with this structure, we will modify, we will remove this hydrogen or hydrogen from maybe here and here, this will give me up and down structure, and I am also removing 2 electrons. So, its multiplicity will still, charge and multiplicity will be still singlet and it will be neutral, and then I will optimize this structure taking this one as QM and this part as XTB, and then we will calculate the free energy difference. So, this will be your homework problem. The initial geometry for alpha tocopherol or vitamin E, you can download it from here. Now, we have discussed about subtractive QMM coupling. What are its advantages? Advantages is that no communication is required during the quantum chemistry and molecular mechanics routine. So, you can have 2 separate programs for the QM and MM and actually calculate the energy from there and add them up together to get a QMMM value, maybe with a calculator. So, in principle it looks very straightforward, and that makes the implementation is relatively straightforward. So, if you have 2 methods, you can always get a subtractive QMM coupling with it. Disadvantage: first problem is that because I have to calculate the MM calculation for the QM subsystem, I need a force field. Now, many of the cases when I am doing calculation on small molecules containing some kind of heteroatoms or some special molecules, the force field for that may not be available. So, I have to always parameterize it, and one of the reasons that is why I was using XTB for the lower level method, because I do not need to have the force field there. The second problem is that the force field needs to be sufficiently flexible to describe the effect of the chemical changes when the reaction happens. Remember, I have to also do calculation on the small subsystem which is important, which is supposed to be taken in the QM. So, I will do a force field calculation on that also. So, now the force field has to be sufficiently flexible to describe the effect of the chemical changes. So, I need to get a good force field which may not be always straightforward. And this can be particularly problematic for modeling biological charge transfer processes, because they will be usually mediated by the protein environment. So, in these cases there is no straightforward way the main subsystem and the surrounding environment can talk to each other. So, there is no clean cut way. So, sometimes it becomes very difficult when there is a charge transfer from one part from the main subsystem to the environment or environment to the main subsystem to take care of that kind of system, or if you are dealing with an excited state calculation. Remember, the the QM part can be anything, it can be an excited state method also. So, this can be a particularly problematic case where you have this kind of a QM region where some charge distribution is happening. For this kind of thing, it can be particularly problematic, and for that we come to something called additive QMMM coupling. So, what happens in the additive QMMM coupling is that you can write the total QMMM energy as the QM energy, MM energy plus a coupling term which actually connects the QM and MM. In the additive scheme, the QM system is embedded within the large MM system, and the potential energy for the whole system is the sum of the MM energy, QM energy and QMM coupling term. Here only the interaction within the MM region are described at the force field level, and in contrast to the subtractive scheme, the interaction between the two subsystems are treated explicitly. In the subtractive scheme, they were never treated explicitly. So, we were calculating at some kind of energy difference, and this interaction can be described at various degrees of sophistication. So, to understand the nature of the interaction, let us see these pictures one by one, and let us go through slightly carefully. So, in the top 3 panels A, B and C, it shows the interaction between QM and MM region. So, this is the interaction between the bonds. It can be an interaction between the angle, where the QM and MM is attached to an angle, and QM and MM can be attached to a dihedral also. Panel D shows the van der Waals interaction between an atom in the QM region, this one, and 3 MM atoms through Lennard-Jones potentials. These interactions are modeled by Lennard-Jones potential. And panel E mimics the link atom concept, which will come slightly into it, and all of this is happening in the panel where the electrostatic interaction. So, this will act like point charges. So, the QM region will see the effect of the MM region in the calculation as point charges, which is in the case of electrostatic embedding. Now, how I cap the bond, and we were discussing link atoms. So, in a QMM calculation, what sometime may happen is that the boundary between the QM and the MM region will go through a bond, and we have to always make sure while choosing the QM region that the boundary should only go through a single bond. If the boundary goes through a double bond, that will cutting that kind of things will lead to very huge amount of error, and that should be avoided in every cases. So, that as a general guideline, you should never cut a bond which is either double bonded, triple bonded, or somewhere even they are not double bonded, if they are somewhere involved in some kind of a conjugation also, in that case also you should avoid. So, what happened is the link atom method is that you actually cut the bond between QM and MM, and in the place of QM region you just put an and so that means when I cut the bond, my valency will be now changed, right. So, this is, let us say this is an ethane. Now, these 3 atoms like the carbon and this 2 CH2, okay, ethane may not be a good example because I do not have the other hydrogen. Okay, let us think that the other hydrogen is somewhere. So, then I will cut this bond and I will put an hydrogen to cap this valency. So, this is actually called, and similarly I will end the MM region also with an hydrogen atom, and this is actually called a link atom because it links the 2 bond. The link atoms are present only in the QM calculation, and for the MM atom they are generally invisible. So, MM atom will never see it, it does not really matter for the MM atom because the MM atom it does not really matter for the MM region because MM atom does not anyway consider the valency. Sometimes the H is needed to make the end stabilize so that the end does not become very flexible. In principle, each link atom introduces 3 additional degrees of freedom because I am introducing a new x, y, z. So, but what happens is that link atom is placed as a fixed position along the bond in every step of the simulation. So, this link atom distances are never optimized, so that these additional degrees of freedoms are removed because I consider them as fixed, they are never changed. At each step, force acting on the link atom are distributed over the QM and MM atom to make sure that there is no additional force get into this one. And the other way you can cut the bond is using some more sophisticated techniques like a localized orbital or a GHO. So, in both the approaches, what happens is that you does not cut the bond explicitly. So, you just consider the bond exists, but you change the orbital in such a way. So, in a local self consistent field, what you do is that you parameterize a frozen orbital along the QM atom, which orbital contains both the electrons and they are not optimized in the SCF. Whereas, in the generalized hybrid orbital, this orbital is considered in the SCF. So, the main difference in these two is that in this case actually this orbital is frozen. So, I put 2 electrons and I never change it, whereas in this case the QM orbital which is directed towards the QM atom only. So, here only the QM orbitals are optimized and this is left out of the optimization process. So, here what is done is that here I also consider the MM atom, the orbitals on the MM atom which is attached to a QM atom. Now, among the MM atom orbital, the only orbital which is pointed towards the QM atom is optimized, rest of them are actually not optimized. So, depending upon how you are considering the effect of this link atom, the link atom is most commonly used QMM scheme. Although ORCA allows you to do the local SCF model by using a multi-layer modeling scheme, which is called multi-layer DLP, but for most of the purposes QMM is the most commonly used. Now, among the embedding, you can have two kind of embedding. First of all is a mechanical embedding, where all interaction between the two subsystems are handled at the force field level, the QM subsystem are kept placed. So, the MM region actually acts like a support for the QM region, it does not change the explicit Hamiltonian. So, most implementation of the MM embedding, the electronic wave function is evaluated for a QM subsystem and the MM environment that cannot induce the polarization of the electron density in the QM region. So, it is just like it makes the structure of the QM more less flexible. So, it makes it more rigid and that is what is expected. An isolated molecule may be more flexible than what you will see in maybe in a protein cavity. So, that is what this mechanical embedding this MM region do, it keep the structure inflexible. And for the calculation of electrostatic interaction between the subsystem, one can either use a fixed set of charges for the QM region, because finally when I have to calculate the, remember we are discussing what is called an additive coupling scheme. So, I somehow need to calculate the interaction between the QM and the MM region. So, I need the charges. So, the electrostatic interaction between the subsystem, one can either use the fixed set of charges for the QM region given by force field, or one can recompute the partial charges of the QM atom at every integration step of the simulations. So, basically I am anyway calculating the wave function. So, I can use the least square fitting procedure to derive the atomic charges that optimally reproduce the electrostatic potential at the surface of the QM subsystem. Lennard-Jones parameters are not updated. The problem is that if during the simulation changes occurs into the chemical character of the atoms in the QM region for a reaction that involves change in the hydrogen atom of the state, then the Lennard-Jones parameters are supposed to change. That cannot be taken care by this kind of embedding scheme.